Your Toyota is consuming oil right now, and the dealership is counting on you never finding out why. Not because the engine is worn out, not because you drive too hard, but because of a design decision made in an engineering office that created one of the most profitable silent failures in automotive history. And in the next few minutes, I'm going to show you exactly what they built, exactly what they hid, and exactly how to stop it before it destroys your engine completely. I'm talking about the 2AZ FE, the 2.4-liter four-cylinder that Toyota put into millions of Camrys, RAV4S, Highlanders, and Scion TCs between 2001 and 2011. This engine was sold to you as the gold standard of reliability. The benchmark, the reason you bought a Toyota instead of something else. And on paper, it looks like a masterpiece. Dual overhead cams, variable valve timing, forged internals, a compression ratio optimized for longevity. Toyota's reputation was so strong that people bought these vehicles without even test driving them. Just the badge was enough. But inside that engine, buried deep in the piston assembly where no dealership technician will ever show you, there is a flaw so specific, so mechanical, and so completely understood by Toyota engineers that what happened next can only be called a choice. To understand what's happening inside your engine right now, I need to take you somewhere most people never go. I need to take you inside the combustion chamber, down to the level of the piston itself, moving it up to 6,000 strokes per minute, operating at temperatures that would melt aluminum if the engineering weren't precise. Because this story begins not with a defect in the metal, but with a hole. Or more accurately, the wrong size hole. Inside every piston in the 2AZ FE, there are 3 ring grooves machined into the piston body. The top 2 grooves hold compression rings. Their job is to seal combustion gases above the piston and prevent blow-by. The third groove, the bottom one, holds what's called the oil control ring assembly. This assembly is actually 3 separate pieces working together, 2 thin steel rails and a corrugated expander spring between them. This entire system has one job: scrape excess oil off the cylinder wall on every downstroke and return that oil back into the crankcase below. It does this through a series of small holes drilled through the bottom of the piston ring groove, called oil return ports or drain-back holes. Oil gets scraped off the wall, it collects in the groove, it flows through these holes, and it drips back into the oil pan. Simple, elegant, effective. Except in the 2AZ FE, Toyota made these holes too small. The diameter of those drain-back holes in the original 2AZ FE piston design is measurably insufficient for the thermal environment that engine creates during real-world operation. And this isn't speculation. This is physics. Here's what happens. When the engine is cold, oil is thick and viscous. It flows slowly. The small holes are marginal but functional. But as the engine reaches operating temperature, something changes in the oil control ring land that engineers call coking. Modern engine oils, especially the 5W30 and 0W20 weights Toyota recommends, carry a significant percentage of additive packages: viscosity modifiers, antioxidants, detergent dispersants. When these additives are exposed to the sustained heat of the ringland, which in the 2AZ FE can reach between 200 and 260 degrees Celsius during highway driving, the lighter hydrocarbon fractions begin to volatilize and oxidize. They don't burn cleanly. They polymerize. They turn into a hard, tar-like carbonaceous deposit that bonds to the aluminum surface of the ring groove with remarkable tenacity. Now here's where the restricted drain-back holes become catastrophic. Because the oil cannot drain back fast enough through those undersized ports, it accumulates in the oil control ring groove. It sits there. It bakes. The carbon buildup begins. And as that carbon layer thickens, it starts to pack around the 3-piece oil control ring assembly from beneath. The expander spring loses its ability to push the rails outward against the cylinder wall. The rails themselves, which are only about 0.4 millimeters thick, begin to lose their radial tension. This process is called ring sticking, and once those oil control rings are stuck, they stop scraping. They just sit there, dragged along by the piston, doing nothing. Without the oil control rings functioning, every upstroke of the piston carries a fresh film of oil up into the combustion chamber. That oil mixes with the air-fuel charge. It burns. And because it's burning incompletely, it contributes to further carbon fouling on the piston crown, the intake valves, and the spark plugs. Your engine is now burning oil, and the diagnostic symptoms are almost invisible at first. Maybe a faint blue tinge in the exhaust during cold start, maybe a smell. Maybe nothing at all until you pop the hood and discover you're a quart low after 2,000 miles. But the damage doesn't stop there, because now we enter the second stage of destruction. When the oil control rings stop functioning, the thin lubricating film on the cylinder wall is no longer being managed correctly. Instead of a precisely metered uniform film that prevents metal-to-metal contact, you start getting an inconsistent coating. In some areas, the wall gets too much oil. In others, the oil burns off completely. The cylinder wall, which was honed at the factory with a specific crosshatch pattern designed to hold just enough oil for lubrication, begins to glaze. The microscopic peaks and valleys of that crosshatch fill in with combustion byproducts and polished away by the ring assembly dragging without proper tension. A glazed cylinder wall cannot hold oil. It becomes nearly frictionless in the wrong direction, meaning the compression rings above also begin to lose their seal. Now you have blow-by. Combustion gases push past the compression rings into the crankcase. You get crankcase pressure. You get more oil contamination. The whole system unravels in a cascade that mechanics call the death spiral, and Toyota knew. Not suspected. Knew. Because in 2007, they released Technical Service Bulletin number 0094-07, and then they updated it, and then they extended the coverage. And then they quietly issued revised pistons with enlarged drainback holes as a running production change. The same engine, the same casting number, but with drain holes that were measurably larger in diameter than the originals. They fixed the hole. They just didn't tell anyone who already owned the engine with the broken one. The business model built on this silence is staggering. An oil consumption complaint on a 2AZ FE that walks into a dealership generates, at minimum, a multi-step diagnostic process that Toyota itself outlined in its own repair procedures. A series of consumer tests where you drive a specific mileage, return, and they measure the shortfall. This process takes weeks. Then, if confirmed, the repair involves removing the cylinder head, decarbonizing the ringlands, and in severe cases, replacing the pistons entirely. The parts and labor cost for a full piston replacement on a 2AZ FE, depending on region, runs between $2,500 and $4,500. Multiply that across the hundreds of thousands of affected vehicles, and you have a warranty and post-warranty repair market worth hundreds of millions of dollars. They did not build this engine to fail. But when it did fail, they built the repair infrastructure before they built the public solution. The evidence for the redesigned piston is not anecdotal. Fleet operators running 2AZ FE-equipped vehicles, particularly taxi and rideshare fleets in markets like Australia and Southeast Asia, where this engine was extraordinarily common, documented the oil consumption issue with the precision that only high-mileage commercial use can provide. Some fleets reported consumption rates of 1 quart per 1,000 miles in engines with fewer than 80,000 kilometers. The same fleets, after performing ringland decarbonization and installing Toyota's revised piston assembly, reported normalized consumption, meaning undetectable loss between standard service intervals for the remainder of the vehicle's operational life at mileages exceeding 300,000 kilometers. The fix worked perfectly. It worked the first time. It was available years before most owners ever knew there was a problem. Toyota's own internal part supersession records show that the revised piston part numbers replace the originals as the standard service item. If you order pistons for a 2AZ FE today through a genuine Toyota dealer, you will receive the updated design. The enlarged drainback holes are there. You can see them. You can measure them. The acknowledgement is built into the parts catalog. They just never sent a letter. So here is what you need to do, and I'm going to be exact, because vague advice costs people engines. If you own a 2001 through 2011 Camry, RAV4, Highlander, Scion TC, or any vehicle equipped with the 2AZ FE, start by establishing a true baseline for your oil consumption. Not the dealership's baseline, yours. After your next oil change, mark the dipstick with a paint pen at the full mark. Drive exactly 1,000 miles under your normal conditions, not babied highway cruising, actual normal use. Check the dipstick. If you have lost more than a quarter of a quart in 1,000 miles, Your oil control rings are already showing signs of degradation and you need to act now, not at your next service interval. The first intervention is chemical and costs under $15. It is not a magic pour-in fix. It is a ring-land cleaning protocol using a product called Liqui Moly Ceratec, or more specifically for this application, Liqui Moly Pro Line Engine Flush, added to the old oil before your drain. Run the engine at idle for exactly 10 minutes, not more, following the product instructions precisely, then drain while hot. This removes soft carbon deposits that have not yet fully hardened. If you catch the problem early, before the rings are fully stuck and before cylinder wall glazing has progressed, this protocol, combined with a fresh fill of full synthetic oil meeting Toyota's WS or equivalent specification, can restore partial ring function. Do not use this approach as a substitute for mechanical inspection. Use it as a diagnostic. If consumption improves measurably after the flush in fresh oil, the rings were stuck. If consumption does not improve, you have progressed to glazing and you need a mechanical solution. The mechanical solution is a ring-land service. This requires removing the cylinder head, which gives access to the pistons from above after the head is off, though some shops perform a full drop depending on their preference. The piston crown must be cleaned with a non-metallic scraper and a dedicated carbon solvent, taking extreme care not to score the aluminum. The ring-land grooves must be cleared of all carbon deposits, and the drain-back holes must be probed and cleared individually. A thin wire or a drill bit one size below the hole diameter is used to clear blockages without enlarging the hole geometry. The original rings, if not scored or broken, can sometimes be reused if the cylinder walls have not glazed. However, if glazing is present, the bores must be honed to restore the crosshatch pattern before any ring will seal correctly. If you are already into that level of work, installing the revised Toyota Pistons with the enlarged drain-back holes is the correct permanent solution, and the cost difference between reusing old pistons and installing new correct ones is negligible against the total labor. Already committed. Source the revised pistons through a Toyota dealer or a trusted OEM supplier, and verify the part number against Toyota's current supersession list for your specific application. The engine code is stamped on the block. The date code matters. Know your exact variant before ordering. Going forward, run this engine on nothing shorter than 5,000-mile oil change intervals using full synthetic, and do not extend beyond 7,500 miles regardless of what the maintenance reminder says, because the oil degradation in a compromised ringland environment accelerates additive depletion faster than the algorithm in your dash accounts for. Use a filter with a bypass valve rating appropriate for cold start conditions in your climate. In colder regions, a 0W20 full synthetic in winter reduces the viscosity spike at cold start that strains already compromised ring sealing. And if you want to go deeper on this, if you want access to the torque specs, the specific part number cross-references, the step-by-step decarbonization procedure with photos, and the community of people who have already performed this repair and documented their consumption test results before and after, come find us in the KURO Cars community. There are members in there with 2 AZ-FE engines running clean at over 280,000 miles after performing exactly what I just described. Real data, real results, not forum speculation. The knowledge to protect your engine exists. It has always existed. Now you have it. Share this video with every person you know who drives one of these vehicles. Because the next time a friend gets quoted $4,000 to fix oil consumption in their Camry, they deserve to know that the answer was always a $15 flush and a set of revised pistons that Toyota redesigned a decade ago. The industry built the problem. We built the solution. And in the next video, I'm going to show you something that will make today's story look mild. I'm going to show you the TSB that was never released publicly, the one that explains why certain 2GR FEV6 engines were consuming coolant from the day they left the factory, and why the fix requires something Toyota will never recommend but costs less than your last tank of gas. Hit the bell. Do not miss that one.